we had talked about how to use this. So if I wanted to determine if something was nonpolar using the electronegativity,
I don't
You
think
froze. I don't think we looked at that.
Yeah, no,
oh,
we didn't
get
go
to
over
that.
that.
Huh? Okay, so let me give you the breakdown. But we did look at this, right?
The table? I don't think you. I
No,
don't think you showed it to us.
Okay. See, I'm glad you got to keep me on my toes. I just start saying stuff and then. Okay, so that means that we probably did we talk about polar, non-polar? Did I tell you my story with the PlayStation and my sister?
Yeah, you mentioned that.
Okay, so this is just basically showing us how sharing occurs, right? So if it's even sharing, you're going to have equal pull on both sides. They're going to share the electrons, right? Evenly. In the situation of a polar bond, what happens is that the electron spends more time here. So then that guy is going to get a little bit bigger because it has another electron added onto it, right? And this guy is going to get a little bit smaller, oops, because that other electron is on the other side on that other element, okay? And so that's kind of showing you that unfair pull. And then I'm going to use this as an opportunity to write some stuff down here. So you guys know how to use the greater than and less than sign. Pac-Man eats the bigger one. You guys don't know what Pac-Man is. Okay, so when we're trying to determine the electronegativity, or if we're trying to determine numerically which bonds are going to be polar or nonpolar, and you're looking at bonding between two different elements, we're going to use the values that are shown on the electronegativity table. So, show you these values. Okay, so this is the electronegativity table. You guys are going to have this. I'm going to put it in your resources, and you're going to have access to that, okay? Now, the thing about when you're calculating if a bond between two atoms, and you're trying to determine who's going to be more electronegative, or if you're going to have, like, or I should say, the type of bond that you have. Is it a polar bond or is it a non-polar bond? The way that we do that is by looking at the values of the elements on this table. So for instance, if we have carbon bonded to hydrogen, now we want to see if these guys are going to be sharing evenly or unevenly. The way that we would do that, we would take the difference between the two electronegativity values. So carbon is 2.6, and hydrogen is 2.2. And we subtract these guys from each other, and that value is 0.4. So then if that value is less than 0.6, then it's going to be nonpolar, meaning they're going to be sharing evenly. If that value is between 0.6 and 1.8, then it's going to be polar. And then if that value is if that value is greater than 1.8, it's going to be an ionic bond. And we know ionic bonds simply by nonmetals interacting with metals, right? That's the simplest way of doing it. But if we want to try to put numerical values on it, this is how we'd go about it. So our value here is 0.4. So is that going to be a polar bond or is it going to be a nonpolar bond?
Nonpolar?
Nonpolar. So let's say we're looking at oxygen and fluoride. A bond between these guys. So what am I going to do?
You're gonna subtract them.
Okay.
And
So fluoride
fluorine
is,
was 4.
sorry.
Okay.
And oxygen?
I can't see it, but is it 3.4?
3.4. Sorry. I guess that big red line in the middle of it is kind of blocking the way.
Just a little bit.
Okay, is that going to be polar or non-polar?
Polar.
Okay, simple.
With the chart, yeah.
Yeah, with the chart, it makes it so simple, right?
If we get tested on this, will we be able to print out the chart?
Yes, the chart is, that's one of your tools.
Okay, thank you.
Okay, so everybody got this down up here?
So for example, if the answer to one of them is like 0.6, it'd be polar. And if it's 1.8, it would still be polar, correct?
That is correct.
And if it's like 1.9, then it'd be ionic. And if it's 0.5, it'd be nonpolar.
That's correct.
Okay, just want to double check. Thank you.
No problem. Oops. Going the wrong way. Okay, so let's clear this. Okay, so we've talked about the electronegativity. And if you look at it, there's a trend, a general trend. Now, there are always going to be exceptions, and you guys will recognize there will always be one element that is going to be that exception, you know, or something along those lines. Here we got a couple of them. But if you look at the trend generally, as we go from left to right, it's going to be increasing in terms of electronegativity. As we go from top to bottom, it's going to be decreasing in terms of electronegativity. And you'll notice, you know, these guys here are closer to the noble gases, right? And I gave you a general rule. I said, if you're close to a noble gas, you're going to have a strong electronegativity. Well, yeah, they have a strong electronegativity, but it's based upon that period that they're in, right? So if you actually look, oxygen, which has a 3.4 value for the electronegativity, is stronger or has more energy or more more desire to pull the electron than chlorine does, right? Because chlorine is a 3.2, right? So, you know, you have to kind of pay attention to the table. And so when you're doing things, like when you're trying to determine who's going to go in the middle, the center atom is always going to be the one that is the least electronegative. Except for oxygen, except for hydrogen. Hydrogen will never be in the center. So, oops. Least electronegative will be in the center. Okay. Piece of cake? Good. Jason, you look like you're like, there's something, you have something, you're thinking about something.
Well, when I was in tutoring earlier, not with one of your tutors, but at the Hartnell tutoring, the tutor mentioned that Another exception is that generally carbon will go in the middle.
Yes,
Okay.
yes. Carbon's a whore. Carbon likes to have 4 attachments if it can. You know, it's a little bit of a swinger. It likes interaction. It likes action. So
Likes to have one on each arm, huh?
exactly. Yep.
And this is pertaining to like Lewis structures or the symbols?
Yes. Yes, this is
And
pertaining to Lewis structure.
the bonds to them.
Yep. When we're talking about the covalent bonds, yes. Okay.
Yes.
Okay, so when we talk about bonds, we could have multiple bonds. We've talked about a single bond when we're sharing just one set of electrons. If we're sharing 2 sets of electrons, or a total of 4 electrons altogether, 2 pairs each, right? That's a double bond. And a triple bond would be sharing 3 pairs of electrons. Okay, so let me give you an example. Because, you know, if I talk about it, you're like, what the hell is he talking about? Show me a picture. Okay, so let's say we have fluorine, right? We know that fluorine gas is diatomic. So how many valence electrons does fluorine have, each fluorine?
7.
Okay. So for them to reach their octet, having 8 around each one of the fluorines, sorry, I lost my edge there. How many electrons do they need to share?
1
This
pair.
one, right?
Okay. So we draw that line, that represents our bond. That's a single bond. Okay. So let's look at oxygen. How many valence electrons does oxygen have, each one?
Six.
Okay. So what can I do? So that's a total of 6 plus 6 is 12. So I have 12 electrons to work with. What can I do so that each one of them will have 8 electrons around them?
Make a double bond and leave 4 electrons on each.
Okay. So you're saying something like this. Oops. Okay, so that's 2, 4, 6, 8, 2, 4, 6, 8. Meets my goal, and that's a double bond where we're sharing 4 electrons. And then what about nitrogen? How many valence electrons does nitrogen have?
It has 5 valence electrons.
So we have a total of 10 electrons to work with. So what can I do to make nitrogen so that it has 8 around it, each one?
Triple bonds and leave 2 electrons on the outside.
Okay, so that's 2, 4, 6, 8. That's 2, 4, 6, 8. Piece of cake?
Yes.
Good.
So all of them are supposed to end up with 8?
In most cases, there will be some exceptions.
Okay.
And we will talk about some of those exceptions. Oops. Did everybody get that?
Yes.
Okay.
Yeah.
Okay, so we know that there could be more than one atom that are forming compounds, right? We don't always have to have a diatomic molecule. We could have a polyatomic molecule, right? So like water. So in the case of water, if we look at it, hydrogen has 1 valence electron, oxygen has 6 valence electron, and this hydrogen has 1 valence electron. So if we want to sit there and satisfy each of them for their octet, hydrogen only wants to have 2 around it. Then it's just like helium. That is going to be the most it has around it. It will never have more than 2. Okay? Kristen, are you there with me? Okay. And we know that oxygen wants to have its 8. So we're satisfying oxygen's octet. Okay? Simple. And then here's an example with ammonia. So how you guys are feeling about this so far? Do you think you can do Lewis dot structures?
I think, yeah, I think that if I go back to the chem homework, I was doing the chem homework yesterday, and I
Yep.
noticed that it gets a little bit more complicated when you're working with more elements. So I was
Yes.
wondering, let's say you have like 3 elements, right? Like for one of these examples, but you throw in sulfur, the hydrogen elements would, the molecules would bond to the oxygen instead of the sulfur, right?
In some
Would-
cases, yes. It depends
Oh,
on the
okay.
molecule that we're talking about. And we're going to talk about that, I promise you. I know exactly
Okay.
the one that you're talking about, right?
Okay,
We're
perfect.
talking about the one that was H2SO4.
Yeah.
Right?
Yeah.
Yeah. And I promise you, we'll do some of those problems because I'm going to go over something that normally at the level that you guys are at, I won't go over, but it starts to make sense if you actually see it. And I won't hold you accountable for it. You know, if you can get me a Lewis dot structure that works, I'm going to give you points. Because right now, the level that you guys are at the level of intermediate. You know, I expect you to have a certain level of knowledge. I don't expect you to be at the level of general chem yet. You know, we're building you up for it. But if you guys know it now, when you get to the level of general chem, you'll be like, yeah, I got this. This is not a problem, right? So, but I promise you I would get to that. Just one second. So let's say we have, we'll start off some simple ones. CO2. N2O. Okay. And I need one more. Let's do this one.
I think last time we did CO, CO2, and N2O.
Oh, we've already done these?
Just not the C2H. Is that what it is?
Okay.
So maybe some new ones.
Oh, you want some new ones? Okay. See, that's, you know, I just stick them in my head and they just keep popping up. So then you want to be challenged. That's what you're telling me, huh? So let's do this
I
one.
want to make sure I understand it well. So I guess, yeah. I hope everyone's on the same boat.
Well, I am, because I was going to say we did those.
That's good.
Okay, thank you. I don't want to be the only one here.
See, let's do this one.
Wait, are all those together?
Yep, that's one. That is one compound.
Okay.
And I'm going to give you a little bit of a hint to kind of help you out because the way it's written, it tries to help us figure it out. Okay. And then let's go ahead and do this one, since we've talked about it already. Aren't you excited for that one? That was, who was it? That was, let's see. Get the
That was
voice.
me.
Brian.
That was me.
It was David.
David.
Okay, David. Okay, so we'll do that one. Okay?
Perfect.
And let's do one more. I'm gonna add one more. I'm gonna add one more from the homework. I think it was POCL2. All right, PLO. I think this is it. Okay. Let's do this. Let's make it a little more challenging. Hold on. There you go. Okay, so if we're adding an electron, what does that mean that we're going to do?
Doesn't it mean we're gonna subtract if we're adding?
If we have a negative value there, what does that mean?
Oh,
One more
We're
electron.
adding,
So we're adding an additional electron. If it was a plus value there, then what would it be?
we would
What would you
remove
do?
one.
Okay, piece of cake?
But
Yes.
where would you add it on to?
The center atom. You started, I always try to put everything on the center atom first, you know?
Okay.
And remember, because the electrons are mobile, right? So they're going to be able to move, and you're just trying to find what is going to be the most stable structure that we can get. And I'm kind of building you guys up to understand the stable structure. And we're going to talk about formal charges, okay? I'm getting you to that point. Even though I usually don't talk about it in this class, but you guys are, I think you have another level, you know? So I'm going to see if we can get there.
As long as you don't put it on the exam, that's okay.
I agree with that.
Okay, so you guys ready to go in groups? Okay, how did it go?
Complicated.
Complicated.
I couldn't keep up. I was like so lost.
It's just, a lot of it is going to be practice, and you guys will get the hang of it. And in your kit, you guys have those little cutout widgets. I don't know what else to call them. Did you guys start cutting out your widgets so that you could put your bonds together? And
Not yet.
Not yet.
so that's one of those great tools that you guys are given that you could use to do your structures. Another thing that works really well are marshmallows, different colored marshmallows. Get the multicolored pack, and then you can use that to help you get your structures. And then it'll also start helping you understanding the 3D component of it. Okay, so let's talk about it. Since you guys, we have what? We have 30 minutes. I have 20 minutes.
Oh, my back.
We have plenty of time. Okay, so let's start with the first one, the easy one. C2H2. What is the secret? What am I going to do?
Put the carbons in the middle.
Put the carbons in the middle. Oops, wrong two.
You're thinking of H4, huh?
Yeah, I used it on another test, so. Oops, I didn't mean to say that. Okay. I was trying to figure out why I don't have any annotate. I'm on the wrong screen. Oops. Okay, now I'm having troubles all the way around. Is my screen not showing anything?
No, it's
Just
just
showing you.
Just showing me? Okay. Come on. Come on, come on.
a little mad.
Okay. Can you see it now?
Yeah.
Yeah.
Okay. Good. Here's my eraser. That's why they were looking at me like I was crazy earlier. Just kept adding hydrogens. Okay. How many bonds?
3.
Okay, so we know that carbon, each of the carbon has how many valence electrons?
8. Oh, well, valence, it's 4.
And there's 2 carbons.
Yeah.
Okay, and hydrogen has how many valence electrons?
1.
So I have a total of 10 to work with.
Yeah.
Yeah.
I need to make sure that I have 10. All right, so that's 2, 4, 6, 8, 10. Okay, I'm good. Now, each of the carbon have 8 around them. 2, 4, 6, 8. Okay, that's good. This carbon has 8 around it. 2, 4, 6, 8. That's good. Each hydrogen has 2 around it. 2, 2. We're happy. Okay, let's do this one next. P O C L.
I have a question. So for the previous one, or I guess any problem that's like that, do you do the triple bond just because it looks cleaner than having all those lone pairs surrounding it?
Yeah, well, you use the bonding. It looks better. You could
Okay.
technically put all of your dots in here, so that could be 6 dots in there. It would still mean the same thing.
Yeah. So
Is that
it
what
wouldn't
you're
be
saying?
wrong. Yeah, it wouldn't be wrong if you put those lone pairs, but it just looks better in this way because it looks cleaner.
Well, you also want to get in a habit of using the line. The line
Okay.
starts to mean something, and this is also kind of getting you guys ready for organic chemistry, which we're going to touch on next, our very next section with chapter 13. We're going to dabble in organic chemistry.
Okay, thank you.
Can I give the next one a try?
You sure can.
Okay, let me. Because that's the last one we were doing. We didn't get the chance to finish it, but I just finished it. So I just want to make sure I understood it correctly. So I have P. Okay, in the center. Oh. Am I writing?
Yep, you are.
Hold on.
It stalls a little bit.
Oh, it froze on me. Okay, hold on.
Yeah, I've been having trouble with Zoom all day today.
Okay, this is my funky looking P. And then I have oxygen. And then, oh, come on. There we go. Chlorine. Doot, doot, doot. And chlorine. So then, do you just want me to write down what I kind of did, or give
Yeah.
you my process, or my results?
You can tell us along the way, you know.
Okay, well, I got, oh, I just, oh, come on. Oh my goodness gracious, great balls of fire. 1, 2. Okay. Sorry, can you guys see these over here?
Yeah.
Okay. And then I have 4 on oxygen over here. And then I have 2 on top of the P, or the phosphorus. And then I have 6 valence over yonder. Okay, so that's what I got. And the reason why P or phosphorus is holding more than 8 is because it can hold a maximum of 10 from what you were telling us earlier.
But if you don't have to, why would you do it?
Because I can't put them anywhere else because then all the other ones will have more than 8 valence electrons.
Let's see. What if we move this back over here?
Oh.
Would that work?
4, 6, 8. But then we're oh yeah. 2, 4, 6, 8. Okay, let me delete it.
Wait,
I didn't even think about that one.
If
What
we're
was that?
instructed to follow the octet rule for every, if we're instructed to follow the octet rule for every single molecule, then we would make sure to have 8 valence electrons for phosphorus, right?
That is correct.
Okay.
And then if you're not instructed, if it says formal charges, and that's what I'm going to show you next.
Okay.
You guys can't run out of the room yet. I know you
Okay.
want to.
So
So-
formal.
What was that?
I have a question. So it's Cl2 and then to add another electron. So where's the added electron in that you're doing, Jennifer?
She added it towards the center, and then that allowed her to get all of the bonds, right? So like, for instance, phosphorus
Where?
has, we'll count them. Let me count them.
Oh, okay, sorry.
Okay. So phosphorus has 1, 2, 3, 4, 5 valence electrons, right?
hmm
And then oxygen has 6 valence electrons. So that's 1, 2, 3, 4, 5, 6 around it. And then that extra one is being added to make that bond. So we've already added it around that center atom.
Oh, okay.
Okay. Does that answer your question?
Yeah. Thanks. You did a good job, Jennifer.
Thanks. It took me a while, but I got it.
Yeah,
Appreciate it.
cool.
It makes me so proud.
Yeah.
Pushing each other and positive energy. That's great. I like that. Okay, so let's do formal charges before we move on to the next, because I think we're getting close to that, the closing time moment. So formal charges are going to be, I'm going to type this out for you. It's going to be and you're going to look at it for each atom. It's going to equal the number of valence electrons minus
Repeat
the
down,
number
Jackson.
of lone pair electrons minus the number of bonds.
Formal.
Okay.
Jackson, mommy's writing.
She just wants to learn chemistry. It's okay. How old is she?
Jackson?
Yes.
Sorry, he looks like a girl because
I'm sorry. How old is he? My bad.
It's okay. He's 2.5.
2.5.
Yeah.
So by the time he's 4, he's going to be balancing equations.
He's gonna be a chem pro. Jackson, look, can you say hi? Over here, look, you say hi. No, you too shy? Yeah.
Okay, so let's take a look at the oxygen. So if we go with the formal charges, how many valence electrons does oxygen have normally?
6, normally.
Okay. And then how many lone pair are around the oxygen?
6.
And how many bonds?
1.
Is that correct? Check my math.
Yes.
Okay, phosphorus.
Oh, I can't see it. Jackson, sit
How?
down.
What is the number of valence electrons that phosphorus has?
5.
How many lone pair electrons are around this phosphorus?
2.
And the number of bonds?
3.
This chlorine?
Chlorine has 7.
7 lone pair. Sorry, 7 valence electrons. How many lone pair?
6.
And how many bonds?
1.
And the other one would be exactly the same thing. Okay, so this is called formal charges. Now, at the end of the day, if I added up all of the charges together, it should equal the charge on that compound. So 0 plus 0 plus 0, minus 1. Does that equal minus 1?
Yeah.
Okay, so that's one way of doing confirmation. The other thing is, with formal charges, you want your numbers to be as low as possible. You want them to be minus 1, 0. Ideally, the best molecule, the most stable molecule, if there's no charge here at all, is the one that has 0, 0, 0. Okay, for each of the formal charges. Now,
So
if you have a 2 or a minus 2, that's probably not the best structure. It exists, but it's not stable. Okay, so this structure can exist and not be stable. So then what happens is the electrons will move till it gets to the point where it's stable. When you're at 0, 0, 0, that is the most stable you can get. Okay, if you have a minus 1 or plus 1, that's close, and it may be what the best you can do. But if you can get to a 0, 0, 0, that's going to be your best structure. Okay, so let me show you how this is used real quick on your homework assignment.
I have a question.
Yeah.
For, I guess this formula you just gave us, for example, if it was POCl2 with a 2 minus, would our answer need to be minus 2?
Yeah, so the final answer would be need to add up to minus 2. Yes.
Okay.
Okay. Yeah, I've been lazy. I haven't been doing my homework.
Wow.
I know. How do I expect to pass this class?
Wait, did we go over CH3COOH?
We haven't gone over it yet.
Okay.
I wanted to show you this first, and I wanted to give you an example because I know we're running out of time.
Okay, thank you.
I think it was question 33.
Was it 33?
Yeah, I was trying it right now. It was told me I had.
This is the one I wanted. 41. Okay, it says a Lewis dot structure for a bromate, shown down here, is shown below. However, its formal charges are not minimized. Starting with this structure, complete the correct structure with minimized formal charges. Okay, so if you look at it, everybody's happy. All the octets are full, right?
Mhm.
Everybody has 8 around them. They should be doing celebrations, handstands, and everything, right? But the formal charges lets us know that if that molecule is going to be stable enough to exist, right? Or otherwise, the electrons are going to continue to try to find the lowest energy level. okay? So this guy isn't stable because it's formal charges. I'm going to show you a cheating method. You could just hit formal charges. That has a formal charge of 2. This guy has a -1, this guy has a -1, this guy has a -1.
Oh,
That 2 is kind of the anomaly. You don't want anything like a 2 unless it's absolutely a must. So that means that we can sit there and change this around a bit, sit there and try to get to the point where we have a low or a minimized formal charge. So I'm going to show you how to calculate the formal charge for this guy, and then we'll do the movement. Okay. So, or actually, I won't show you how to calculate. You guys will calculate the formal charges. So what is the number of valence electrons around the bromine?
7. Oh, yeah.
Okay, and the number of lone pair
2,
electrons, and the number of bonds.
3.
We're just checking their work because sometimes they do make mistakes. Okay, the oxygens, and they're all going to be the same,
6.
right? So we have 6 valence electrons. How many lone pair electrons?
6.
Okay, sorry, my screen is flashing and I can't see what I'm writing. And then
1.
number of bonds.
1.
So,
-1 for all of
so
them.
all of these guys would be -1, right? So that just proves that.
Mhm.
Now, let's do some movement. And we know that bromine, where's bromine located on the periodic table?
On the
Which
number
period?
30, atomic number 35, period 4.
Period 4. So it's below period 3, right? And we know that any element that is below period 3 has the ability of using the d orbital. So that means that it can actually it can have more electrons around it. Okay. So it's flexible. It could have more than the normal 8 around it. So let's go ahead and see what we can do to make things happy here. Let's see. So if I click on my oxygen here and I change the number of lone pair electrons, then I click on my bond, and that allows me to have a double bond there. Okay, so let's look at this oxygen here. What is its formal charge? Sorry. How many valence electrons does it have?
6.
How many lone pair electrons?
4.
And then how many bonds?
2. 0.
Oh, that's a pretty good one, right?
Mhm.
Okay, so if we could do the same, and let's look at the bromine now. Bromine has how many valence electrons?
7.
How many lone pair around it?
2.
How many bonds?
4.
Okay, so that still has a value of 1. Is there any way that we can make it smaller?
Yeah. You can add another bond with another oxygen.
Okay,
Remove the 2 pairs, make a bond with bromine.
okay. And if you look at it, you notice how the formal charges change on it
Mhm.
as you make that adjustment.
Mhm.
And then if you look, remember I told you it has to add up to a -1 since we have a -1 up here.
Mhm.
So this is the best that we can do. So this would be the best molecule with the lowest amount of energy.
Got it. Do you think that, would you rather have the oxygen be more negative than the bromine, or would you have?
Yes, that is a very good question. So who do you want to have the negative charge, right?
Mhm.
You want the guy who has the most electronegativity to have the negative charge. If you remember that table, oxygen has more electronegativity than bromine.
Okay.
So that is a very good idea. The one with the least electronegativity is the one that you want to have positive charge if you have a positive.
Okay.
Okay, so that's great. I'm glad you just led us right into the next part. Okay, questions?
Cash?
Definitely, I'll take it. I take Venmo.
Oh, I do have one question.
Yep.
Regarding the atoms that can utilize the d orbitals, you said
Mhm.
anything above period 3. Would that include period 3?
Yes, period 3 and above. Yeah, so
Period 3
phosphorus,
and above.
sulfur.
Okay.
Yeah, because that's where you start the 3D, right? Because D starts at 3. And so then you're able to use all of those, it's kind of like extra chairs. You bring in these extra chairs for that row.
Okay, thank you.